Here we go with your homework questions. These are on factoring using the quadratic formula for imaginary roots, looking at how to deal with fractional exponents, and a question about a geometric series. So here we go. First, we have f of x equals x squared minus 6x plus 9. Can you factor this? Find the zeros, right? Where does this graph cross the x-axis? And where does this cross the y-axis? So go ahead and pause the video, see if you can answer those questions. And here is the solution. So we're going to factor first. First we're going to factor. We have x and x. Negative 3 times negative 3 equals positive 9. Negative 3 plus negative 3 equals negative 6. And so here we have a double root, right? This function equals 0, or the range here equals 0 when x equals positive 3. And that is true in both of these cases. And so we have a double root. And what does that mean graphically? Well, we go to our 0, x equals 3. And it's just going to bounce, right? It's going to bounce off this point. It's not going to cross. It's not going to cross, right? If it did cross, it would have to come back up at some other point, right? If it did cross, then it means it has to come back at some other point. And, you know, we don't have another point for that to occur at. We just have one single solution. And so this is what we call a double root, and it just bounces, okay? So that's where it crosses or touches the x-axis. We also want to know, where does this function cross the y-axis? Well, in that case, we set our x values equal to 0, right? So we say f of 0 equals 0 squared minus 6 times 0 plus 9, and that equals 9. So this function will cross the y-axis. Looks like I didn't make it quite long enough. At y equals 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And so it will cross through there. Right. So we have a y-intercept of y equals 9. And we have an x-intercept at x equals 3. All right, next question here. Next question. We're going to use the quadratic formula to figure out what the roots are, potentially imaginary, of the following quadratic. So again, pause the video here, see if you can come up with the two solutions. And if you need a little help, here is the work solution, right? And so we have our a value, our b value, and our c value. That's 1, 3, and 8. So we plug those into the quadratic formula. We get negative 3 plus or minus 3 squared, 9, minus 4 times 1 times 8 minus 32 divided by 2 times 1, or 2. This equals negative 3 plus or minus square root of negative 9 minus 32, negative 23, divided by 2. All right, so it looks like we do have an imaginary root here. Why is that? Well, because we have a negative here under the square root. How do we deal with that? We remember, if we have a negative under the square root, in this case, square root of negative 23, that's the same as square root of negative 1 times the square root of positive 23. Remember, the square root of negative 1 is I times the square root of 23, right? And so we're left here with negative 3 plus or minus the square root of 23 times I divided by 2. Now we have two scenarios, a plus scenario and a minus scenario. Negative 3 plus the square root of 23i over 2. Negative 3 minus the square root of 23i over 2. Finally, if we put this in complex number form, we like it in the form of a plus bi, right? The imaginary part separate from the real part. And so we just need to separate these two so that there's a real part and imaginary part. So the first one, negative 3 over 2 plus square root of 23 times I, right? The I is outside of that, divided by 2. And the second one, negative 3 over 2 minus square root of 23 times I over 2. And there's our answer. Next question here, we're going to have a string of 6 questions here. Now looking at fractional exponents. So the first 3, I'll write them all out. Third root of 5, square root of 3 to the 5th, and the 5th root of 2 to the 7th. And what we want to do here is convert these into exponential form. So exponential form, right? No radical, right? This is called the radical, right? We don't want a radical. Take that away. So go ahead and try these out. Once you've done that, here are the solutions. So remember, if we just have a radical, that is equal to something to the 1/2, right? If we have a 3 in the radical, that's equal to something to the 1/3, right? A 4 in the radical, that's equal to something to the 1/4, and so on. So the first one here, we take whatever is under the radical and raise it to the 1/3. Right, done. Second one here. First, we're going to deal with what's inside, right? PEMDAS, parentheses first. So deal with what's inside. Well, 3 under the radical is going to be 3 to the 1/2. And that's still raised to the 5th. Now, an exponent raised to an exponent, we multiply. So this is equal to 3 to the 5/2. Finally, similar case here. 2 under the radical, the 5th root of 2, that's going to be 2 to the 1/5. And that's still raised to the 7th. So that's 2 to the 7/5, right? We have 1/5 to the 7th, so we multiply exponents when exponents are raised to exponents. And there you go. Here we're going to work in reverse. So we're going to go from exponential form into radical form. Right. Now we do want the radical. Remember again, radical equals something to the 1/2. Third root equals something to the 1/3, etc. So here it's as simple as the third root of 6. Right? Those are equivalent. Okay, here, remember when we have 10 to the 5 over 3, the bottom number goes into the nook here. The top number goes above. All right, so we have 10, right, the third root of 10 raised to the 5th. Okay. Here we have a negative exponent, so we simply remember 1 over 10 to the positive 7/5. Right? Now we can treat this like our rule above. 5th root of 10 to the 7th. Done. All right, finally, we're going to consider and remember a geometric series. So consider the series 3, 6, 12, 24, 48, 96, and so on, right? There's 3 letters that we care about. A, this is our indexing. A1 is 3, that's our first term. A2 would be 6, that's our second term. A3 would be 12, our third term, and so forth. R, this represents our geometric ratio. So what number do we multiply each time to get to the next term, right? That's times 2, times 2, times 2. So R equals 2. And then N. Sometimes we use N, sometimes we do not. N simply refers to how many total terms are we going to have, right? That could be a number of your choice. Maybe you just want 10 numbers in this sequence. Maybe you want infinity, right? N could be infinity, right? So that just means number of terms. And that's up to you, okay? And we consider 2 things here. One for a sequence, one for a series. Remember, a sequence is simply the list. 3, 6, 12, 24, 48. The series sums up the list. So a series would be 3 plus 6 plus 12 plus 24. Right? When we are looking at a sequence, we have the following formula. A sub n, so the nth term, the term at the nth location. So if you're looking for the 100th term, but you don't want to write out 100 of them, you can use this formula to find it. It's equal to the first term times the geometric ratio, right? What you're multiplying by each time, and that is raised to the power n minus 1. So if I asked you to find what is the 13th term, well, go ahead and try that, but you simply plug in here. What is the 13th term in this sequence? It starts with 3 times 2 to the power 13 minus 1. The 13th term is equal to 3 times 2 to the 12. I'm going to use my calculator here. 2 to the power 12 is 4,096. that times 3 is 12,228. So the 13th term of this sequence is equal to 12,288. All right, so you can see if you wanted to write all these out, if you wanted to continue multiplying by 2, you can definitely go ahead and do that. You'll get to 12,288 by your 13th term, but using this formula is going to be a lot easier. Right? So there's not really a practice question here, but I really want you to be able to be comfortable using this. So you should be able to recognize this formula and when and how to use it. Next is for a series, and maybe I'll write it down here, series. So this is the sum, right? Not just what is the number value at the 13th place, but what is the sum of the first, second, third, fourth, fifth, all the way to 13th term. If I add those all together, we have another formula for that. That formula says the sum of the first n number terms, the sum of the first n terms is equal to the first term times 1 minus the geometric ratio to that term's power, divided by 1 minus the geometric ratio. Okay, so again, maybe we'll choose the 13th term. What is the sum of every term up to and including the 13th number? Well, we just plug it in. The first number is 3 times 1 minus r to the 13th. I should say 2 to the 13th. Divided by 1 minus 2. So the sum of the first 13 terms equals 3 times 1 minus, and I'll use my calculator, 2 to the power 13, 8192, divided by negative 1. So we have 3 times 1 minus that, negative 8191 divided by negative 1. And you can see our negatives are going to cancel, so we're going to get a positive value. And dividing by 1 doesn't change the value, so we're just going to multiply by 3. And so we get 24,573. So the sum of the first 13 terms is 24,573. Okay, and again, this isn't really a question I'm asking you to solve in the moment, but what you should be able to do is recognize when and how to use this formula, right? This sums the first however many terms you want. This one simply identifies a value at any location you want. That's it.